Hi guys. Today we're going to be doing atmosphere, climate, and weather notes. So let me get started with this. Move this guy. First thing we should know about the atmosphere is what it is. We need to know the different layers. There's 4 main layers. So we say it's a thin envelope of life-sustaining gases. We'll be talking more specifically about the gases and about pollution in the different layers here in the next couple of units. So anyways, your 4 layers, we have the layer that we live here is the troposphere, then we have the stratosphere, then the mesosphere, and then the thermosphere. We don't need to worry about exosphere for this class. Okay, so let's start with the one closest to the Earth, actually where we live. So the innermost layer, again where we live and we breathe, is the troposphere. It extends to about 17 kilometers above sea level. Really important thing for you to know is that this is where most of the mass of all of Earth's atmosphere is contained. You have the most mass, you have the most molecules in this layer. That also has to deal with the pressure, which we'll get to in a second. This is where all the weather occurs. We've already seen a little bit of this breakdown earlier in the year. Atmosphere is mostly nitrogen, 78% nitrogen, 21% oxygen, 1% argon, and a very small percentage of carbon dioxide, and then we'll talk a lot more about that when we get to climate change in another couple units. One thing that you should notice, and we'll look at this in some of our diagrams in a second, is that the pressure always decreases as we go up in the layers of the atmosphere. Okay, pressure always decreases. It says because with altitude, it always decreases because average density decreases with altitude. So the amount of gas, the volume of the gases that you have, is also decreasing. So the pressure decreases. Okay, and then when we get to the top of the troposphere, we have a little thing called the tropopause, and it just says it's the top part of the troposphere. We can see, and we'll look at a better graph of this in a second, that the temperature decreases as we go up, and that's true. If you guys have ever climbed mountains, if you've gone up high in altitude, the temperature decreases as you go up in altitude. When you get to the point where you're going from the troposphere, the lower level, to the stratosphere, the second level, you run into this tropopause where the temperature actually begins to rise all of a sudden, and so we're going to shift back this way. Okay, I'll come back to this picture in a second. Let me get the other layers. So let's go to the stratosphere as the second layer. It does contain less matter than the troposphere, because again, remember, we're decreasing in pressure, we're decreasing in the density of the gases. It's calm air, little mixing. It's where we fly planes. It's very good for flying planes. It's also where the ozone layer is found. We have a whole little mini unit that deals with the ozone layer. Ozone layer is thought of as a global sunscreen because its job is to block out UVB radiation specifically. We'll talk about all sorts of implications with that because we have this protective layer, but we do emit certain pollutants that break it down and can create a hole in it. So what this ozone layer allows for is it allows us and other life forms to exist on the planet. It's a necessary thing. If we were just exposed to all of the UV rays that were coming in, we would be exposed to lots of mutagens and lots of mutations. It protects us from sunburns, cancers, cataracts, and other ailments like damage to the immune system. It prevents oxygen in the troposphere from being converted to ozone because it tries to make ozone up in the stratosphere. And again, we'll learn about that whole process. It's a whole chemical process that happens in one of our next mini units. So ozone layer is currently being depleted. We mostly due to these things called CFCs, but again, I'm not going to talk about that too much in these notes because we're going to talk about that in a couple weeks. Okay, and then let's go back to this diagram actually. So this one's really important because it shows us all the different layers and it shows us what happens to the temperature and the pressure as we go up to the different layers. So this bottom layer is the troposphere. One thing I want you to notice is that the temperature decreases as we go up in altitude in the troposphere. And then you hit your tropopause, actually right at the top here, right as we're going from troposphere into stratosphere. you have the ozone layer. So ozone layer is actually technically at the bottom of the stratosphere. In the stratosphere, we actually see temperature rise. Okay, and then we have a stratopause before we get to the third layer. The third layer is called the mesosphere. Mesosphere, we see a pretty severe decline in the temperature again. Okay, and then we hit the mesopause. And then we see an extreme increase in temperature. And the reason for that is because this layer is going to be, towards the exterior of our atmosphere, and it's exposed to all that UV radiation coming from the sun. So it gets very, very warm up there. The other thing I wanted to show you here is the pressure. What happens to that as we go up in altitude? Pressure, we said at the lower levels, is higher. And then again, if you guys have ever climbed mountains or you've ever gone up in altitude, you realize the pressure does decrease, oxygen levels decrease. It can make it a bit more difficult to breathe. You may get short-winded a lot more easily. So anyways, as we go up in altitude, even in the troposphere, the pressure decreases. And as you continue all the way up these different levels, the pressure continues to decrease. Okay, and so here's your atmospheric pressure. So we can see the pressure is highest when we're at the bottom. It decreases as we go up. Okay, just a couple more diagrams. So before we get to the last couple layers, we'll just talk about what weather is. We said weather does occur down in the lower layer of the troposphere. The weather is just your day-to-day changes. It's what you check weather.com. If you're like me, I check that almost every day to see what the temperature is going to be like, what the humidity, what the percent precipitation is going to be like. Is it going to be sunny? Is it going to be cloudy? What's the wind direction and wind speed? Those are your day-to-day conditions. Those can be measured with weather balloons, aircraft, radar, and satellites. Okay, and going back to your layers, the third layer is the mesosphere, which we already talked about. The fourth layer is the thermosphere. And as we said, heat in that top layer it's really, really hot because it's exposed to all that solar radiation. Also, the only other cool thing about the thermosphere really is that this is where the northern lights occurs. If you're up in Iceland, you guys are tired of hearing about Iceland or any of those northern latitudes, they can experience the aurora borealis during their winter time, and that's caused by glowing of ions in the thermosphere. Okay, we also need to know about what happens to incoming radiation from the sun. We've already talked a little bit about this at the beginning of the year, and I'll just kind of show you this diagram just to kind of refresh your memory. Here's 100% of incoming solar radiation. There's going to be a lot of different things that can happen to it. So, this says here that a quarter of the sun's energy is going to be reflected back to space by the atmosphere itself, while another 1/4 is absorbed by gases in the atmosphere, so reflected and absorbed. Some energy is reflected back due to what's called the albedo effect. We'll talk about that more when we get to climate change. That's just the phenomenon when you have a white or a light-colored surface, it's going to reflect light, whereas a darker surface would absorb. So on our planet, areas that are snowy or sandy will do reflecting of the light. Some light is absorbed by darker surfaces, which would actually aid in heating the planet. A small percentage of incoming light is used for photosynthesis. And then outgoing energy is actually transferred into a different form of energy. So the incoming energy is the UV radiation, little tiny wavelengths, and then the outgoing stuff is going to be really, really long wavelengths that can really warm up our inner atmosphere, and we call that infrared radiation. Okay, so the infrared radiation gets re-radiated, gets bounced back, and that gets trapped in the atmosphere and causes the greenhouse effect. But again, we'll talk a lot more detail about that in a couple weeks. And here's just a graphic again showing you all the different things that can happen. Some of it's reflected by the atmosphere, some of it's reflected by clouds, some of it's reflected by Earth's surface, some of it's absorbed by atmosphere, some of it's absorbed by clouds, some of it's absorbed by the land and the oceans. And eventually all of this energy will be re-radiated back outward in the form of that long wave infrared radiation. Okay, so we already talked about weather. We said it's the day-to-day conditions, whereas climate is long-term weather patterns. Okay, what drives weather? Well, weather is driven by that uneven heating of the Earth's surface. We've kind of talked about that before. We said that the sun's going to hit mostly at the equator, okay? Hits mostly right here, and that's going to drive these convection cells, which you see back here. They happen all over the Earth's surface. It causes the moving around of air, so it says it causes warmer air to rise, cooler air to sink. That just causes air masses to move around. This creates global circulation patterns for air. That's what drives all of weather. It's just the incoming sun, how it hits the planet. Okay, so we're going to talk a little bit about weather. Weather's not that big of a deal in terms of like the test for your class, but it's good to just have a little bit of background understanding of how this stuff works. So we'll start off with air masses. Here are a couple of different types of air masses that would affect us. Air mass is just said to be a large lump of air that's going to have similar temperature and moisture level throughout. So if we're looking at the U.S. here, the green chunk of land, we are exposed to maritime polar air masses. And those are going to be, maritime just means water. So this is going to be cold water, cold air masses from the water that can hit us from both the west and the east. We can also experience continental polar, which again you can imagine that's going to be cold air masses coming from on land, from above. Okay, and then similar to that is continental Arctic. So obviously those are all cool. If it's continental, it's probably going to be a dry air mass. If it's polar, it's going to be a moist, wet air mass. Then from the south, we can get hit with continental tropical, which again would come from land and it would be hot and dry. Or we can get maritime tropical, so that would be hot, warm, and moist coming from the water. Okay, you can also have different types of fronts when these different types of air masses meet up with each other. So you've got these warm air masses and these cold air masses kind of circulating the planet. You get what's called a cold front. We always hear the weathermen talking about this on the news. These are the ones that are going to generate the exciting stuff, like your storms. Okay, so this is when a cold air mass rushes up on a stationary warm air mass. And that is going to quickly push that moist air upward. It's going to quickly push the warm, because we know warmer always rises, so it's going to quickly push it up on top of this cold air mass. Quick rising is going to cause big cloud formation. That's going to give you thunderstorms. That's going to give you rain. That's going to give you kind of your more exciting, violent weather. And then a warm front's a little bit more boring. It says this is when a warm air mass collides with a stationary cold air mass. Okay, so here you get kind of your slow, gentle rising over this cold air mass. It's not that really quick uplift. It's kind of a slow, gradual rising. These are those days where it's like the whole sky is just those really thin gray clouds, and you just get that warm, steady rain drizzle kind of all day long. Not very exciting. I'm not a big fan of those types of days. I'd much rather have a nice thunderstorm or something. Okay, then we can have high and low pressure systems as well. And again, not that huge of a deal because I don't have enough time to go into huge detail with you guys about this. But again, it's just kind of good to know what these things mean and what the background is behind it. So if you hear weathermen talking about high pressure system, that's going to be a system where you have an air mass descending. And you can see here it's descending out from the center. And when that happens, that air mass is going to be warm and dry. Okay, so when it's high pressure, the air mass is warm and dry, and you end up getting nice dry weather. So if you hear a high pressure system's coming in, that means there's probably no clouds in the sky. It's very, very dry. There's no precipitation. And then I wanted to touch on a couple other issues that can cause dry air as well. You can also get dry air, and you pretty much always see this with mountains especially, when you have a leeward and a windward side. The windward side is going to be the side of the mountain that receives the wind, it receives the weather. It's usually going to be a rainy, windy side of the mountain. And then a leeward side is going to be the opposite side of a mountain, and you usually always see deserts on the opposite side of the mountain. And this effect is called the rain shadow effect, and I'll show you a picture of this on the next slide. So like I said, the windward side of the mountain is where you're getting the wind and the weather, and then on the opposite side, you've already kind of squeezed all the moisture out of that weather, so a lot of times on the opposite side, you're going to get really, really dry conditions, and because of that, you usually have deserts. Okay, and then I gave you one more reason why you can have desert or dry air in deserts at a certain location. At 30 north and 30 south latitude, when we're talking about convection cells, you also have that dry, cool air sinking at 30 north and 30 south. So these are all different scenarios where you can get dry, cool air sinking, and you get very dry conditions because of that. So let me show you the rain shadow effect. So this is showing, on this is the windward side of the mountain, as I was saying. The mountain is going to cause the air masses to rise, and when it causes the air masses to rise, they're going to cool and they're going to condense. When they condense, they form clouds. When they form clouds, they're going to rain. So you get a lot of rain, a lot of weather stuff happening on the windward side of a mountain. And as I said, that air mass pretty much gets all the water squeezed out of it. It's almost like squeezing out a sponge. So then when it gets up over the mountain, that air mass is really, really dry. So that dry air mass just kind of sinks, and you get this really dry condition over here. So this is called the rain shadow effect. So again, windward mountain, we see a lot of rain and weather. The leeward mountain, you do not. It's very dry. Okay, low pressure is the opposite of high pressure. So if low pressure had descending air masses, if high pressure had descending air masses, low pressure has ascending air masses. And this is also called a cyclone. So this is actually creating a cyclone here. And when you have this air mass starting to rise, it's going to cool and condense. And like I said, when an air mass cools and condenses, it's going to form clouds. And clouds a lot of times are going to give you rain and storms. So low pressure, when you hear a weatherman saying that we have a low pressure system coming towards us, that means we're looking at some rain and some storms. Okay, some weather extremes. So these are actually some extreme low pressure systems. One is a hurricane. Okay, hurricane, big, huge cyclone. It's a tropical storm. It forms out over the ocean. The warmer the ocean is, the warmer that water is, usually the more severe they say that those hurricanes are going to be. We know normally the hurricane season is in like late summer, early fall for us. They form down in near the equator, and they can make our way up our coast. So we said the winds get really, really powerful with this, greater than 75 miles per hour. And obviously there's a lot of destruction. There's a loss of life of organisms and humans, tons of damage to property. But there are some good things, and we can talk about those some more in class since I'm trying to get through these notes so they're not too long. Okay, and then another severe low pressure would be a tornado. Okay, so again, it's that cyclone type cloud formation that occurs. So here you have that cold, dry air collides with the warm, moist air, causes really, really quick, steep rising, causes that cyclone, causes that funnel cloud. And again, we know the effects of tornadoes. Again, loss of life, lots of damage to property, but it's just a really severe low pressure system. Okay, this is a cool graphic because it shows you where we're most vulnerable to tornadoes and hurricanes in our country. So here you have your little tornado alley, especially out here in the Midwest. Highest is red, so there's good old Kansas, your Midwest states. You got some red sprinkled in there. Actually, there's some up in Pennsylvania too, and even down in the South. And the rest of them, they don't even have any, looks like. And then hurricane frequency, mostly Gulf. Okay, a lot of the Gulf gets hit pretty badly by hurricanes. Up the East Coast, there's us. So even though, we don't live on the water, we do experience the effects of hurricanes with those storms, as we saw this past year from Sandy. And then we have some hurricanes coming down here. So they form down in the equator, and they make their way up the coast. Okay, so climate we already distinguished from weather. We said climate is the long-term average precipitation and temperature. It's determined by several different things, and we're getting ready to go in a little bit of review of stuff we've already seen. Latitude, altitude, ocean currents. We've already seen a couple of these graphics, so I'm going to try to go through them quickly. Okay, so we've already seen this. We said climate is determined by how much precipitation and how much what the temperature is over a long-term time. So it's the average temperature, average precipitation. These things are influenced by your latitude. You know, are you 0 degrees? Are you 30 north, 30 south, 60 north, 60 south? Altitude, how high up above sea level are you? And then ocean currents, we'll explore that a little bit more today as well. And then this has an effect on a lot of different things. Okay, this is a pretty cool graphic because it shows us what the climates of different countries have been designated. So I thought it was kind of cool to kind of look where we are. We're over here. If we look at the key, we're kind of right between like warm temperature and cool temperature type climate. You can see what they designate other things. Obviously, anything right near the equator, they're calling it tropical. Your yellows are dry, so kind of cool how that follows that 30 north, 30 south pattern pretty well. Highland, you have those. Upwelling, we'll talk about that in a second. You have polar, subarctic, cool. So that's a pretty neat graphic if you want to go back and look at those. And then it also shows us where we have warm ocean currents and cold ocean currents. And we'll talk more about ocean currents when we get to water stuff in a few more months. But here you can see all these red ones are the warm currents. The Gulf Stream's important. We're going to talk about that here in a few. And then we have cold ocean currents coming, especially up from Antarctic region. But you also have some that come down from the top as well. Oh, there's a little one. Yeah, the Labrador. So those are all moving around different air masses, and that affects climate. Okay, so we've already talked about this again. So what actually dominates our climate is the uneven heating of Earth's surface. Okay, that's going to move air masses and water currents, which is going to, again, move around, spread the temperature differences around. Here's your convection cells that we've already talked about again. So remember 0, you have rising air masses that would then sink at 30 north, 30 south. So you have lots of precipitation at 0. Lots of dry, cool air masses at 30 north, 30 south. Lots of desert. 60 north, 60 south, you have, again, a lot more precipitation and then a lot more forest. And then all the way at the top, 90 north, 90 south, again, you have dry because you have sinking air masses. Here we can see something that's an effect of what we call the Coriolis effect. We'll get to that in a second. That causes special types of winds called the westerlies and the trade winds. Okay, I skipped through that. Seasons. What causes seasons? Seasons are caused by the tilt of our planet. So if we look at this diagram here you have the sun and you have Earth rotating around it. Let's take a look at winter. This is what our planet would look like for us in winter. We are tilted backwards. We are then further away from this main heating area, which would be like right in here. That's when we would experience winter, and we said some areas really, really far north actually experience those days of darkness. Spring would be the planet is back to normal tilt. It's not tilted towards or away. It's right on target. So instead of having a solstice, instead of having a winter solstice, we have a spring equinox, meaning that you have a day where it's the same amount daytime as it is same amount nighttime, or same amount sunlight as it is darkness. And then summer, we are tilted towards the sun, so we get more warmth, more sunlight beaming directly on us. And you would have your summer solstice there, or you have your longest day in summer. And then in fall, again, the planet evens its tilt back out. You've got a fall equinox, where you have a day that's the same length daylight, same length darkness. Coriolis effect. So it says, since we have the Earth on this tilt, it's actually going to cause the air masses to not just go in a straight direction. It actually causes them to have this little curve, and they actually curve in a different direction in the upper hemisphere than they do in the lower hemisphere. And we get these cool little winds that are generated from it. You get these little winds called the westerlies and the trade winds, and they're kind of historical because they helped sailors to kind of move back and forth between, let's see, I wrote it down. It allowed for a round-trip trade route for European ships returning from South and Central America in the West Indies, so they could go back and forth between the Caribbean or South and Central America to Europe very easily because these trade winds, you had winds that would blow you this direction and winds that would blow you that direction. And again, that's due to the Coriolis effect. Okay, ocean currents, again, we already kind of talked about those. Very similar to air masses, so they get heated up at the equator and then they move either north or south to spread the temperature that way. Or they get very, very cool at the extremes, at the poles, and then they move towards the equator. So again, they work just like air masses to kind of spread those different temperatures around the planet and create those global systems. Okay, we've already looked at that. Okay, so here it just says ocean currents affect climate. Differences in water temperature, winds, and the rotation of the Earth create these currents. And again, they redistribute heat. Something that's really important, I do want you to know about this, because this is a very important current that you know about, is the Gulf Stream. And the Gulf Stream has a really important impact on Europe, because Europe is at such a high latitude that it would normally have a very, very, very cold climate, especially in a place like England. But because you have this warm Gulf Stream that rides up the west coast of Europe, it's going to really create a much warmer climate there than what they should really have for the latitude that they're at. So if you come back here, you can see that. Again, here's your Gulf Stream bringing heat this way. It's going to really, really warm up this area. And if climate change happens and we have, shifting of ocean currents, they say that could really, really have an effect on Europe. Okay, and then we have something that's called upwelling. Upwelling is created when trade winds blow offshore, pushing surface water away from the land. The outgoing surface water is replaced by nutrient bottom water. So let me see if I have a good picture of that. Oh, I do. Good. Okay, so as we have these currents, and again, a lot of times they're kind of convection cell looking, you get wind that moves this surface water, usually probably warm water, from the surface. It moves it further out to sea, and when it moves it further out to sea, you get this cool water that's down here at the bottom of the ocean that usually has a lot of nutrients in it. It's able to rise up here, move in, and take the place of this warm water. So what you end up having is you have a lot of these nutrients rise up. You have a lot of phytoplankton rise up. That's going to be great food for the fish, which is great food for the birds. And you get a lot of diversity and just a lot of nutrients and a lot of great life along these coasts where upwelling occurs. And again, it's because the wind blows that warm water away and allows this cool, nutrient-rich water to come upward. Now, this has a lot to do with El Nino, which is the last thing we're talking about today. El Nino, which they sometimes called ENSO, which is El Nino Southern Oscillation. It occurs every 3 to 5 years. It takes place out in the Pacific Ocean off to the west coast of South America. I'll show you a picture of that because there are some of the people who get hit the hardest, especially like over there in Peru. They get hit pretty hard. So what happens is that these prevailing westerly winds, we already kind of talked about the westerlies and the trade winds and stuff, they weaken or stop. It's just a cyclic thing. There we go. It's a cyclic thing. Like we said, it happens every 3 to 5 years, and the prevailing westerly winds aren't blowing as hard as they normally do. What this does is it does not move the surface waters away from the west coast of South America and North America. It does not move those warmer waters away from the coast like we just showed on this last slide. So it would not be moving the water this way. So what you end up having is you end up having warm water just sits on the coast. Okay? So you just have warmer water that sits on the coast. It's not being blown west. Normally you would have the upwelling happening like we said here, and Peru would get really great nutrients, have really great fish harvest like of anchovies and stuff. That's going to all stop. Okay, so the normal upwelling stops. It says this prevents nutrients from coming up that normally support algal growth that feed anchovies and other important fish. This reduces the population of some fish species. It can have global effects all over the planet. It says it could also cause severe weather in other places. It can cause storms in the U.S., especially in California. It can cause drought in Southeast Asia. It's not just a localized thing. It's going to affect the whole planet when El Nino goes down, but the people kind of most critically affected are right there on like the west coast of Peru. So let's look at a picture here. So this is showing what normally happens. We said normally you've got this nice wind blowing this warm water off of the west coast of South America here. So all that warm water's coming this way. It's going to make a little convection cell, so you get all your rising air, you get precipitation. Then the air comes back, it gets cool, and it sinks back down again, and we've got this nice little system going. Okay, so that goes on for a while, and again, when it blows that warm water out, the cool water is able to upwell and bring a lot of nutrients up with it. Okay, when this gets disrupted, when El Nino occurs, we don't have those nice strong winds blowing the warm water off the coast anymore. And in fact, it says the warm water flow is actually stopped or even reversed. So we can have water just kind of gets trapped here, or it's actually pushed into the coast of South America. So here it says warm water deepens off the coast of South America. When that happens, you're not able to get this cold water to come up and upwell. Put an X through it. This is not going to upwell. You're not going to bring nutrients up. You're not going to be able to get all your great fish stock that you normally have. This is going to cause drought in Australia and Southeast Asia. This is going to cause storms over here in the U.S. Okay, so it has a global effect. Okay, so again, this picture is going to show you some of the places that are most hit by El Nino. Here's our west coast of South America. So they can get really bad rainfall. Over here we get drought, more rainfall, really warm periods in these areas. So it affects several different spots of the planet. Okay, and then La Nina, it says La Ninas follow an El Nino and are characterized by cooling trends. La Nina brings more Atlantic hurricanes, colder winters in the north, and warmer winters in the south, and an increase in tornadoes. So when we experience a La Nina year, that's a lot of times when we get those really bad snowstorms. And in fact, I believe that the year that we got really bad snowstorms, I think it was 2 years ago, they said that was a La Nina year. And we are not in El Nino or La Nina this year. That's why we haven't been getting anything too drastic this year or last year. Okay, so I'm going to go ahead and finish the notes for today, and we'll do air pollution next.